So the second talk this morning is by Claudia Fevola, who will tell us about the Euler discriminant of complements of hyperplanes.
So much. Is this working? Maybe not yet. It's working? Okay, awesome. Yes. So many thanks to the organizers for inviting me to speak here. It's a great pleasure. So this is an ongoing project with Saclay, Matsubara. The paper is not on the archive yet, unfortunately, but the content, so the mathematics is done, and the paper will be soon available to be read. Okay. So I guess we all like or have to like integrals. I like generalized Euler integrals, and in this talk, this will be restricted to having linear forms in the integrand. So the notation is the following. So this is the variables are denoted alpha 1 to alpha k, and we will think about them as variables on a k-dimensional torus. And the form we take is the canonical form on the torus, and the I are linear forms that we will look at them as linear forms in their coefficients and their variables. So we're not going to fix any of that. And so in particular, the Z, I, J's will be the coefficients, and the alpha will be the variables. And the integrand of generalized Euler integrals is usually a multivalued function. And what makes them multivalued is the set of complex exponents that these have. So there is a natural hyperplane arrangement defined by the linear forms appearing in these integrals that I will denote by AZ. And this is, of course, a family of hyperplane arrangements. So AZ will denote the one for a fixed choice of Z. And as I said, these are multivalued functions. So to make sense of the integrand, of the integral together with the choice of a cycle, you need to choose a branch of your multivalued function. And this is what is done by the theory of twisted theorem, homology, and cohomology. So gamma will be a twisted cycle on the complement of the hyperplane arrangement. So AZ will be the arrangement, XZ will denote the complement of hyperplanes for a fixed choice of Z. And it's very debatable what's the name of these integrals. So sometimes they're called Mellin integrals, ahypergeometric integrals, Omotto-Gelfand integrals, so that we make sure everybody's happy. So there will be two matrices that will play a central role in this talk. There is the monomial support matrix that I will denote by A. And this is a matrix which is sometimes called the Cayley configuration. Not sometimes, it's called the Cayley configuration, which is written as follows. So see the indices, they go 1 to k for the variables, and then k plus 1 to n. So in total, we have n. So if we think about this, here we have n hyperplanes given by the coordinate axis and the actual hyperplanes. And here we build these matrices by looking at the monomial support of each hyperplanes. So the columns of each of these matrix, AI is given by the monomial support of the corresponding hyperplane. And then we attach some rows of one in the matrix here. And then the second matrix that we care about is the coefficients matrix. So this will be denoted by Z. And again, it's the matrix in which each column gets as entries the coefficients of the hyperplanes I introduced on the first slide. Okay, so the motivation comes basically from Austin talks and from cosmology. I'm not gonna dare explain the physics of it. This will be a Lagrangian free version of what was said earlier. So the question in cosmology that cosmologists want to answer is, what is the origin of the structure in the universe? And we've seen that the type of graphs that you can find in theoretical cosmology papers are these ones. And there is a perturbative version of the theories in which, as in Feynman integrals, you can have an expansion of some integrals that you want to compute. And in general, so here n denotes the number of these type of the gray edges in the graph. And so you sum over all graphs G that are undirected connected graphs with n external legs and L loops. And so in this talk, I will try to introduce these psi G as purely mathematical objects, and in particular the ones in flat space, as it was done in Austin's talk. And also, let me say that, so these are the integrals, so this was said before as well, but in case you were not there, these are the type of integrals that cosmology use. But for the purposes of this talk, we actually care just about the black part of the graph. So they're graphs in the familiar way we're used to think about. And the motivation for these pictures come from the fact that like time plays a central role in cosmology. Okay, so how do I think about the flat space wave function? So for me, it's an object, it's a rational function associated to a graph with vertices set V, edges E. And now I will fix the sides of the vertex set to be n. Then psi G is a rational function that just has linear forms in the denominator. So this will be linear forms in these, sorry, I forgot to introduce that there are these variables that we will think about them as complex variables associated to vertices and edges in the graph. And so the HI are linear forms, and P is a polynomial of higher degree in these variables. And we've seen two of the ways, at least I think all of them were mentioned already in the previous talk. So there are three ways you can introduce this function. One is via Feynman rules. So you build an integral associated to these graphs. This will be an integral with respect to the variable representing time. And then carrying out this integration will give you this rational function. Another way is via the canonical form of the cosmological polytope. And the idea is really, this object was introduced in this paper by Nima, by Arkhanyan, Benincasa, and Postnikov. And the idea, I think, it's to introduce an object, so a polytope, whose canonical form is precisely the rational function that was given by the Feynman rules. And the cosmological polytope as a purely mathematical object was later picked up also by Kuhn and Monin and Juncker, Kubitze, Solus, and Venturello later on, in which triangulations and phases descriptions were studied. And the third way you can use to introduce this function is using the recursion formula that was given before. And so this is to say that there are two descriptions which are very combinatorial for describing this rational function. And luckily, the first two ones were introduced before, and I'll briefly tell what is this representation as the canonical form of a cosmological polytope. So the advantage in this setting is that the adjoint hypersurface, so the numerator of this function, it's hard to compute as the adjoint hypersurface of the polytope. And this is a polytope that lives in the real space with cardinality dimension of the vertices plus dimension of the edges. And the nice part about this description is that the the facets of the appearing in the denominator are very easy to describe. And they're in bijection with subgraphs of G. So given a subgraph G, we denote BH and EH is a set of vertices and edges. So these linear forms can be obtained using this formula. So you sum over variables obtained corresponding to vertices, and now you just need to pay attention applying this. While, so let me say that if instead you use, for instance, the recursion formula, you get also the numerator more easily, just summing up all of these rational functions you get in the last step, but then you don't know. So you have a candidate for, it's not a candidate for the adjoint hypersurface of the polytope. Okay, but so we care about integrals. So this type of integral, this family of integrals were introduced in this paper in the case of trees, and later were also like, so their differential equations were studied also in the case of graphs with cycles. And so the recipe to construct the integral is the following. So you take the object, so the rational function we have introduced before, and shift the variables corresponding to the axis. So these were the ones corresponding to vertices. This will be shifted by new set of variables alpha I. And these alpha I, they become the new integration variables. And so there is a normalizing factors appearing here. And the alpha I will appear with an exponent epsilon that we've seen before. Describes different cosmology. So cosmology is interested to like different values of epsilon here. Okay, so so these integrals now are in the shape of the ones I showed on my first slide. So they're generalized Euler integrals. And the first example we can look at is this two-side chain that we've seen before as well. So the rational function in this case is 1/3 linear forms. And these are indeed the 3 linear forms that define the faces of the cosmological polytope in this case, which is a triangle. And in fact, the adjoint hypersurface is just one. The integral becomes the following. So the xi gets shifted with alpha I. And we add these factors. And then these are the matrices that I introduced earlier in this case. So the matrix A is given by 3 main blocks, if you want, corresponding to each of these hyperplanes. So these represent the monomial support of this guy, where I'm looking at it as a polynomial in the alpha. So this represents this term. This is alpha 1, alpha 2, and here we have this term and alpha 1, and so on. And then there is a matrix of coefficients here, which is the following. So 1, 1, x1 plus x2, and so on. However, in my first slide, the integrals were introduced in a more general form than that. So the linear forms now I can actually, before parameterizing them with kinematics parameters, I can have something a bit more general in which I just fix the monomial support, but I don't ask for any dependencies among these coefficients. So there is, we've seen this before as well, there is a hyperplane arrangement associated to this integral, and this is the picture in this case. So as I said, you need to remove the coordinate axis, and then this will be the yellow line corresponding to this one, the green line, and the blue line. And the question I'm interested together with psi A is for which values of x1, x2, and y the number of bounded regions in this real arrangement is smaller than 4. So for example, if I take y equals 0, the number of bounded chambers become 3. if I choose, so this is due to the fact that this yellow line moves here. And if I take x2 plus y equals 0, then the green lines move on top of the alpha 2 axis, and I actually get 2 bounded chambers here. Why do I care about this? The motivation is its connection with the number of bounded chambers, with the Euler characteristic of the complement of hyperplanes. And so we've seen this also in the last slide of yesterday's first talk. So in the real arrangement, the number of bounded chambers coincides with the sign Euler characteristic. This was Varchenko's theorem, Varchenko's conjecture, later proved by Orlik and Terao, I think. And the reason why I care about these, it's a bit more broad, and it's because the decrease in Euler characteristic characterizes the singularities of the integrals and the singular locus of a D module. And so this will actually be part of a solo author paper by Saclay. And so moreover, the bound on the number of bounded chambers, it's actually known. So there is this result by this 9-author paper from 2012 that tells you that the Euler characteristic coincides with the volume of the convex hull of the matrix A. So this was the matrix of the monomial support, if and only if the point, so the choice of coefficients, lies outside a polynomial in Z. So this is called the principal A determinant, and I will tell you about it later. Moreover, whenever you actually take a choice of coefficients that vanish on the principal A determinant, then the Euler characteristic is smaller than the volume of the convex hull of the matrix A. So how are we going to approach this problem of understanding the drop in Euler characteristic? So for this, the Euler discriminant comes in help. So given Z to be a smooth subvariety of the space of coefficients, then the Euler discriminant is the locus of Z in Z, for which the Euler characteristic is smaller than its upper bound. So this is the That's right. Yes. Yes. So so this is so in general this will be the volume. So the upper bound will be given by the volume of A. And so this Euler discriminant was originally defined by Yesterov in this paper, and then more recently, together with Sebastian and Simon, we redefined it in the context of Feynman integrals. So one first observation. I think that would apply to the GKZ setting. Yes. So yes, exactly. So I think this is the observation. Maybe that might answer your question. So I'll say this first. So whenever you take Z to be the full parameter space, then the generic signed Euler characteristic coincides with the volume of A. And in this case, the polynomial describing this zero locus is known, and it's the principal A determinant. So yes. And in the case in the case we're fixing Z to be any smooth subvariety, then an observation is that it's not obvious that this locus is a closed subvariety of Z, but in fact it is. Okay, so what is the principal A determinant? So there is a definition in terms of resultant, but this is when alternative definition or theorem that it's more amenable for computations, and we like it more. So given P to be, let me call P the convex hull of the matrix A, then the principal Lie determinant is a polynomial that's, so it's a product of polynomials in Z, which is obtained as follows. So the product runs over all facets of the polytope P. And then for each facet, all faces of P. And then for each face, I'm going to determine a submatrix of the big matrix A by just selecting the columns that actually contribute to the vertices of the face I'm considering. And now, for each of these matrices, I consider its discriminant polynomial. And now I'll tell you in a second what is that. Let me say that the principal Lie determinant, so each of these factors has also multiplicities that we will look at later. And so what is the discriminant polynomial? This is something that generalizes the notion of discriminant we're familiar with from high school for quadratic polynomials. And so it's defined as follows. So given the locus of coefficients in the coefficient space for which there exists a set of variables alpha in the torus, such that the polynomial associated to the matrix A, so this will be the polynomial whose monomial support is A, and its partial derivatives with respect to the alpha variables have a common root. And now the A discriminant variety is so this is not necessarily a closed set, so its closure defines the A discriminant variety, and it records the values for which the variety, sorry, this should be C star to the K, is singular. So the variety defined by FA is singular. And so I compute this polynomial. So the polynomial then defining this variety is called the A discriminant polynomial. In the case in which this is of higher codimension than 1, this is set to 1. And so we compute this A discriminant polynomial for each submatrix corresponding to phases and consider the product. This defines the principal Lie determinant. And yes, this definition is due to Gelfand, Kapranov, and Zelensky. So here's one example in the case of hyperplanes. So let me consider this matrix given the monomial support, and the Z2 matrix actually correspond to two hyperplanes that have, so these are two hyperplanes in the plane that have all non-zero coefficients. And then the principal Lie determinant is the product of these polynomials, where the so these linear factors, they correspond to the vertices of the convex hull of the matrix A. And these other black quadratic polynomials correspond to the facets of this polytope. So this is the generic case in which, so let's fix Z to be the full parameter space. So this is the case in which the matrix is precisely as I had it here. So there are no zero entries in this matrix. And then this was known, and you can find it in this book by Gelfand, Kapranov, and Zelensky, that the A discriminant is actually a product of determinants, and is the product of all subdeterminants of the coefficients matrix. So this was, this is in pictures, the examples I had before. This is the case, k is equals to 2 and n is equals to 5. And the volume of A is the number of bounded chambers in the arrangement. And whenever I choose that one of these coefficients will be 0. I expect one of the bounded chambers to be lost. So the new case that we were interested in together with Saclay, so the first case is when we take Z to be the full parameter space intersected with some of the coordinates to be 0. So now I assume that in the matrix of coefficients, some of the Zij will be 0. And in this case, so ideally we want to describe the Euler discriminant. And in this case, this is still coincides with the 0 locus of a principal A determinant. And the reason for that is that I'm basically just changing the monomial support of A, but I'm not restricting to a subspace of the parameter space. And so the first result is that this product of determinants actually holds also in this case, where the only thing I need to pay attention is that there will be some determinants that identically vanish, and these will be discarded. So this will correspond to these non-defective phases that I mentioned before. So these are the cases in which the discriminants, they project to higher codimension. And multiplicities, I'll tell you at the end of the talk. So what is the machinery that you need to develop to prove this? So as we've seen, the main definition relies on knowing the combinatorics of the polytope associated to the matrix A. And for this setting, for this type of matrices that arise from hyperplanes, there are built-in notions for the polytopes with precisely those vertices. So given our matrix Z, we define a bipartite graph G with vertex set V and E, having precisely, so now N for us was the total number of hyperplanes, so coordinate axis plus the H hyperplanes. And we divide the set V into two columns. The column V1 will correspond to the coordinate axis. And if you notice, these are also what index the rows of the matrix, while V2 is the set of, represents the set of columns of the matrix Z. And then you say that, so we have an edge E in this graph anytime that the corresponding coordinate Zij is non-zero. Therefore, the set AG is given by the sums of EI plus EJ. These are standard basis vectors corresponding to EIJ being an edge in this graph. And then PG to be the convex hull of the matrix AG, this is the edge polytope of G. And so if you think about it, this is nothing but precisely the convex hull of the matrix A that we had before. So this is just a different way of basically associating a bipartite graph to the polytope that we need to describe this principal A determinant. So what you need to know is the combinatorial structure of the phases of this polytope. And basically, you can prove that whenever you take a non-empty set of vertices, so you take a non-empty set of the vertices V1 and the non-empty set of V2, then the phase of the polytope is precisely described by that subgraph. And moreover, all of the phases are precisely of this form. So there is a correspondence between subgraphs of the bipartite graph and the phases. And so these results for complete bipartite graph were known and proven by Oshuji and Hibi. And so let me say that in this context, so the first example I showed where you had the matrix with all non-zero entries just correspond to complete bipartite graphs. And so the same theorem that I showed before in terms of non-vanishing determinants can be rephrased as follows. So if you take a connected bipartite graph, then the principal A determinant associated to the matrix AG given by the graph is given by the product of the determinants, where now the condition I had before of discarding non-zero determinants translates as follows. So you want that the subgraph corresponding to subsets I and J of the same size is connected, and star is a condition on the subgraph. So this just translates in a condition on the subgraph. So what I just said is that non-defectiveness that I mentioned before translates in a condition on the subgraph, and also that the change of the matroid, so the matroid associated to the hyperplane arrangement, this one being the Z matrix to which we just oppose the identity, changes whenever the Euler characteristic drops. And the condition on the subgraph is something you can, so it's basically that whenever you take a proper subset here, you want that the cardinality of the vertices which are connected to that is strictly smaller than. So the cardinality of the set here is strictly smaller than the neighbors in the graph. Okay, so here is an example. This is an artificial example, so it doesn't come from physics. This is the graph. So the matrix, for instance, has an entry 0, 3 because 0, 3 is an edge. Here, this would be 0, 5 is not an edge, so it's a 0. This is the associated hyperplane arrangement. So there are 4 hyperplanes. And this is the principal A determinant in this case. So it's just given by all non-vanishing determinants in the matrix. And in particular, each of these factors correspond to a subgraph that verifies the conditions I mentioned.
Say what the exponent is?
No, they will come at the end of the talk, yes. So the other case we're interested in is the case of the Euler discriminant. So in this case, so I'm writing Z always in the same way, but this time it lies in a subspace of the coefficient space, in an actual subspace. And we can define this polynomial. So this is defined very similarly to the ones I had so far. And it is the product, in fact, of the non-zero, non-vanishing determinants in this matrix. And this will be, in fact, the polynomial defining the principal A determinant, the Euler discriminant in this case. So whenever you just need to exclude the degenerate cases in which you have Euler characteristic 0, but elements in the matrix here. So if you assume that the Euler characteristic is strictly bigger than 0 for some choice of Z, then the Euler discriminant is precisely the vanishing locus of this polynomial. Here is the example, and this is where physics actually provide interesting examples to test this on. So this was the two-side chain. This was the cosmological integral associated to it. And this is the matrix that now varies in a subspace. I have to say that, like, in this case, actually, there's no drop in Euler characteristics. So in this case, actually, these coefficients are actually generic. But it's no longer the case when you take more complicated graphs. And the Euler discriminant will be the products of non-vanishing minors here. Again, I'm hiding the notion of multiplicities. But actually now I want to say something about the multiplicities. So one thing we can observe is that if we take the generic discriminant, sorry, the generic hyperplane arrangement associated to this matrix had 4 bounded chambers. And now if we take coefficients, for instance, on this subspace, the Euler characteristic becomes 2. This is 4 minus 2, but it's also 2, so maybe it doesn't help. But for instance, if we take y equals 0, the the bounded chambers here become 3, and that's the exponent here is 1, which is precisely 4 minus 3. This is the slightly more interesting example. That was the 3-side chain. The matrix is much bigger. And these are the factors of the polynomial defining the Euler discriminant in this case. So what I said, what I observed about the exponents in the previous example, it's actually a general fact. So this is a theorem due to Esserov that if you take a face of the convex hull of the matrix A, then the multiplicity can be computed as the difference between the volume, so the generic value of the Euler characteristic, and the generic value of the Euler characteristic on that face. And so this is something that you can do numerically, for instance. So this is a built-in function of a Julia package called pld.jl that was part of the project Principal Landau determinant together with Simon and Sebastian. And so what does this function do? So it computes the generic Euler characteristic. And so sorry, these are not the examples these are not the multiplicities for the examples I showed before. These are the ones for the artificial example I showed at some point. And so what this function does is to actually compute the Euler characteristic on each of these components. And it does that numerically, and in particular, it uses this result so that the absolute value of the Euler characteristic coincides with the number of critical points of the log likelihood function of the polynomial defining the variety x. This was also mentioned in Thomas' talk yesterday. So what does this do is actually sampling points on these components and then solving the critical points equations for choices of coefficients on that component. Okay, however, these multiplicity, they also have a different definition, which is the one that uses the subdiagram volume. So they actually are a product of an index of some lattices, which happen to be 1 anytime for hyperplane arrangements, and this subdiagram volume. So this has a bit of a technical definition. I will go through it. And so this is the following. So given an abelian semigroup, we denote by chi of S is group completion. And then we tensor, so this denotes the tensoring with R. Now, once we have tensor with R, we can take a set of generators. And the subdiagram volume of this abelian semigroup is defined as the volume of, as the difference between the volume of the convex hull of this set of generators union the origin minus the volume of the convex hull of this set of generators. And so what I haven't had, so this is for a general abelian semigroup, so I need to tell you what is this quotient, where Q is the phase that we're fixing. And so S of A mod Q is the sub-semigroup of this quotient generated by the full matrix A and the origin, where this guy is the vector space spanned by Q in Rn. So just to say that this is a bit of a technical definition that I would rather maybe not go through it to compute these exponents. And we couldn't find, maybe it's just a linear algebra task, but it's a bit tricky to for any phase also try to compute these sets. It's kind of simple for vertices, but then it's a bit trickier for phases. So the question was, can we derive this number from the graph? And the intuition behind that is that the Newton polytope of A is not only something that gives you an upper bound on the Euler characteristic and doesn't know anything about the drop, but because of the theorem by Esserov, it's kind of suggesting that the Newton polytope should also know something about the drop in Euler characteristic. Sorry. So it's the theorem by Esserov together with definition. So the definition depends on the phases. And then the theorem by Esserov tells you this number actually knows about the Euler characteristic. So the convex hull of A not only knows about the upper bound, but when you restrict to phases, it also knows about the drop. So one first observation is the following. So if we take H to be the subgraph of G, whose edge polytope correspond to the phase Q. So we're taking a phase and then we take the corresponding subgraph. Then one first observation is that we've seen in the examples that different vertices can have different multiplicities. So if I just take the subgraph H, we're not going to get different information for different vertices. So this means that it's something about this quotient graph that should also mimic a bit of what's happening in the definition of subdiagram volume. So this is an example. So if we take, for instance, so this is about this example. So these are for the two choices of vertices that, of edges that lead to two different multiplicities. So there are just two sets of multiplicities for vertices, either the 3 or 2. And these are the subgraphs which are obtained by A from G by shrinking the vertices in H. And then you can consider the matrix associated to G mod H. So this is the matrix in which you delete the edges, delete the columns corresponding to the edges and also the rows corresponding to the vertices. So this gives rise to these two matrices. And now the way to compute the multiplicity is the following. So if you consider the convex hull of these matrices obtained this way, once adding the origin and once without, then you actually get the subdiagram volume in this case. And so one final remark is that there are, so there is an interpretation of these multiplicities also in terms of multiplicity at the origin of a toric variety. So this is, and that will be the multiplicity of the toric variety associated precisely to this quotient. And there is also like a general, so another question is, can we describe the toric ideal that correspond to this toric variety here? And in this case, thanks to the underlining graph, you can do that. So there is a notion of toric ideal associated to a graph. And in the case of bipartite graph, this toric ideal is generated precisely by basically by monomials, by polynomials associated to the cycles of this bipartite graph. So you consider the toric ideal IG, which is the toric ideal associated to the full bipartite graph, and then consider the one which is no longer homogeneous that you obtain by setting to 1 the variables corresponding to the edges. And this is the toric ideal. So the claim is that this will be the toric ideal whose multiplicity at the origin can also will give you the subdiagram volume. So this is just a different way if you want to compute this number. And probably a bit short on time, but that's all I want to say. Thanks.
Okay, thank you very much. There's lots of time for questions. Yes?
So just one comment is that these objects that you study, I actually studied them like a while ago. They're called root polytopes.
Sorry, I couldn't hear.
So these polytopes, which are on the generated by arbitrary graphs, we call them root polytopes, and they kind of appear in several different contexts. In particular, related to generalized pentaedra. On the other hand, there is even kind of more general version of this story that related in special case to the hydra story. So anyways, I can show you some references, and it might be interesting to see the links. But yeah.
Okay, cool.
But the keyword is root polytope. I think what you call H polytope is exactly what we call root polytope.
Okay. Yeah.
Isn't there an extra minus?
Huh?
Federico, do you have a comment?
I just have the comment that I think they're different. I think you do EI minus EJ and
A little bit.
just gives us
Yeah, right. Yeah, actually, yeah. The only difference is we do EI minus EJ because, but which is the same thing, because if your graph is bipartite, you can switch signs in the same. So basically, EI plus EJ is the same thing as EI minus EJ. On the other hand, when you do EI minus EJ, you can generalize it not only to bipartite graph, but to other, not necessarily bipartite graph. There is a generalization. So they're like a version of this, I mean, more general. We call them root because these EI minus EJs are roots from type A system. And
Okay, thank you.
Okay. Any others? Thank you very much.